So hi everyone, today we are going to talk about the neural networks. So usually, if you want to have a course about neural networks, it may last for a whole semester, if not an year. So in this course, we'll have like 2 weeks, this week and next week, about neural nets. So the title it can only be a very brief introduction. And our reference including the textbook by Efron and Hastie 2016 and Hastie, Tipsrani and Friedman 2009. Both of these 2 textbooks can be downloaded in this link and this link. You have the PDF file, so you can find them. And another very important reference is written by Professor Kuan in 2008, Artificial Neural Networks, which was published in the new Palgrave Dictionary of Economics. And this paper can also be found in Professor Kuan's website here. So, what is neural networks? So, neural net have been around in computer science since 1940s or 50s, but it was introduced to statistics and econometrics in around mid-1980s. Okay, and it was important because neural networks really marked a shift of the predictive modeling. Okay, we want to make some good prediction given some X. We want to have some good prediction on Y. So neural nets move the prediction modeling to computer science and machine learning. Okay, the original idea of neural net, or why it's called neural net, because the original idea was inspired by the architecture of the human brain. So in every human brain, yours and mine, there are lots of neurons inside, and one shock to one neuron, and the neuron will pass the shock to another, or the so-called activate the other neuron, and so on. So and this is how your brain works. It's how we believe how your brain works. And neural net is regarded as a universal approximator, which is that although it is inspired by the human brain, it can do a lot more about that. So one very important property is that, we'll talk about this property later, is that it's a universal approximator. This is a machine which, if you give the machine enough data, you can learn any smooth predictive relationship. Okay, this argument sounds pretty strong. So technically, what we want to say about universal approximation is that mathematicians have shown that there is a great class of different functions can be well approximated by neural networks, and that class is huge. So basically, any function you can think of, as long as you are a normal person, it can be approximated. So it was quite popular. Neural net was quite popular in the mid or late 1980s and the early 1990s. However, that's why we always have a however. The neural net was somewhat sidelined in the mid-1990s. So since mid-1990s, suddenly nobody was talking about neural net anymore. Why? The first reason is that to fit a simple neural net take a lot of computing power. Some computing power which is nothing in 2020 could be huge in 1995. So first of all, that's a true story. Professor Kuan told me before that in his in mid-1990s when he was I plan to say when he was young, but he's still young, right? So when he was very young, so when he wanted to feed a neural net in 1990s, so the first thing he would do was walk to the supercomputer to the university. At that time he was in UIUC. But nowadays, everyone, if you have a laptop computer like this, you can feed a neural net. But 25 years ago, you really need a supercomputer. So it was a huge limitation to the application of neural net. And second, although people always say that a neural network is a universal approximation, it can approximate lots of different things. In practice, we have to find some good empirical work, some good applications, some ideal learning tasks for the neural network. In other words, it will be great if you can find some problem that, okay, you have tried lots of different methods, none of them work, but neural network, that'd be great. However, that kind of thing didn't happen in 1990s. Okay, so anyway, in 1990, what people realized, okay, to feed a neural net, it takes lots of computing power. On the other hand, neural net doesn't work much better than other existing methods, such as the pro-vector machines. We will not talk about it in this course, or boosting. Professor Kuan talked about the boosting last week, right? So in the early 2000s, people found out, okay, boosting was way easier, and neural net didn't do much better than boosting. Okay, so why still consider neural net? It had lots of computing power. So neural net was kind of a nice way to say that is neural net was silent, or a more exact way to say is nobody talk about neural net anymore around that time. The second however in this slide is, in the recent decade, beginning around 2010 or 2011, we means that you and me, everyone in this classroom, we have witnessed that the re-emergence of the neural net. There's somehow some reincarnation now being called something you may heard of, deep learning. Okay, so neural net has a new name, which is cool. People call it deep learning. And we can do lots of neural net now, we can do lots of deep learning now, because first, we have some massive improvement in the computer results. Okay, again, in 1990s, if you want to feed a neural net, you have to go to the supercomputer of your university. But nowadays, all you need is a laptop like this. And second, we did have some innovations. Maybe not as important as the improvement in the computing power, but we have some innovation. But most of all, the most important thing is that, okay, now we have some niches that we have found some learning tasks which neural nets did so well, while other methods not working. For example, image or video classification. Okay, so you can give an image, a figure, a picture to the computer, and the neural net can tell you what it is. Okay, is anyone driving to school every day? So when you drive into a school, okay, you have to stop around the gate of the parking lot, and some camera will take the steel plate, the number of your car, A, B, 1, 2, 3, 4, something like that, and the computer can figure out what number it is. How to work? Neural net. I'm sure it's neural net. So, or you can give the computer some video, and suddenly the computer can tell you that, okay, there are some elements in that video, so Netflix can recommend that video, that movie to this guy and this guy, but not that girl. How to work? Neural net. I guarantee you it's neural net. It can work on speech and text processing and AlphaGo. Now can play Go better than the world champion. Okay, it's how deep learning works. We have found such kind of problem which you cannot work on this problem using random forest or gradient boosting or linear regression. Come on. But neural net works so well in this kind of problems. So in the recent decades, lots of people are working on neural nets right now. Okay, so today we'll talk about some introduction, and next we will talk about some other applications. But it can really take one semester or if not a year to talk about all the detail of the deep learning. So if you are really interested in this, You can either take some other course in anywhere, or you may just knock the door of the president's office and ask the experts. Okay, so I've talked lots of things about neural net. So what is a neural net? Usually, I'm showing you guys a very simple diagram of a neural net. Usually, it's also known as the feed-forward neural nets. Okay, so in this case, we have 13 different inputs or predictors. Okay, maybe I want to talk about this empirical example first. So here, this is what we are working on. So we talk about this in the lecture on the random forest gradient boosting. It's called the Boston data frame. So in the library math in R, we have the median housing value of 506 different neighborhoods or different towns around Boston. Okay, this is what we are interested in, the median value of the owner-occupied homes in thousands. If you look at the data, you'll be surprised. Like around 1978, you can spend like $50,000 US to buy a house in Boston. Now it's impossible nowadays. And we want to make a prediction on the median value of the owner-occupied homes. We have several different X. We have different inputs, independent variables. The crime rate of that town, for example, it is by the beautiful Charles River or not. It is it's a dummy variable 1 or 0. Some politically incorrect variables such as is there a lot of African American in that town? No. Remember that if you are going to the States or Canada, don't call people black. They are African American, or you are in big trouble. Another politically incorrect variable, lower status of the population, 低端人口. I don't even want to talk about what it is. Anyway, so we have several different inputs. We want to make a prediction on the median housing price of that town. And we have the data about 506 different towns. And if you want to fit a simple neural net, it goes like this. So we have 13 different predictors. So each predictor is connected to these 5 hidden units in the hidden layer, or they are also known as neurons. Neurons, 中文应该是神经元. Remember, neural network want to mimic the architecture of human brains. So each input connects to the neurons, the hidden units, and each hidden unit is connected to the output. In our case, the output is the median housing value of one town in the neighborhood of Boston. And we have a cool figure like this. Okay, what is it all about? Let's look at some formula here. So in the previous slides, it's a simple 3-layer feed-forward neural network. We have 13 different inputs. We have 5 hidden units or neurons. If you look at the textbook by Hastie, Shirani, and Friedman, The Element of Statistical Learning, 2009, they would tell you that the 3-layer feed-forward neural network was the most popular one around that time. They also call it the vanilla neural network. Everyone was using it around 2009. Nowadays, people always talk about, when we talk about neural net, usually some occur in people's minds, they were talking about some really deep neural network. We may have many hidden layers, but let's begin with the 3 layers vanilla neural network. Okay, so in this 3-layer neural network, our input is X. We have a model which is Z2. 2 indicated as in the 2nd layer. Z2, L. L is from 1 to P2 in our case. L is from 1 to 5. The Z is a linear transformation of our input. Okay, our input times the WLJ1, take the summation, plus some WL non-1. Then after the linear transformation, we have Z2. And we bring those Z2 into a usually nonlinear function, G. We'll talk about what G is in 2 or 3 slides. Then we have the AL2 here. Then again, we try to bring the AL2 into another linear function like this. W non 2 plus summation L from 1 to P2, which is 5 in this case. WL2 times AL2, we have the Z3 here, and Z3 is our output, the prediction of the housing value. Okay, so what is it? First, we take a linear function, make a linear transformation to our input, bring this linear transformation into the G function, got some A, and bring those A into another linear transformation, and we got it. There are some colorful terms in the neural nets. So those W here usually are known as weights. I have no idea why it's called weights. Those intercept here are known as bias. Okay. The original idea for the neural net should be like this. When we want to mimic the architecture of the human brain, we have some inputs here, but the neural will bring out some information, not from the input by its own. So it's not from the input, so people call it the bias, but it's just the intercept. And the G here is the activation function. It's called the activation function because remember, we want to mimic the human brains, and in human brain, one neuron will activate another through the link. That's why it's called the activation functions. Okay, so we have only 3 layers. Oh, by the way, it's called a feed-forward neural network because we have some other network. For example, there may be a shortcut, which is in the second layer we may also have X in the linear transformation or something like that. But we'll keep everything. We'll keep everything in the basic. We'll talk about only the feed-forward neural network today. Okay, so this is our model, and you can see we have 5 hidden units. In each hidden unit, we have a linear transformation. So in the linear transformation, we have 13 inputs, so we have 13 slopes, 13 coefficients, and intercept, a bias. For one neuron, we have 13 weights and 1 bias parameter. So in one neuron, we have 14 parameters. We have 5 neurons. So in this layer, we have 14 times 5 parameters, which is 70 parameters. In the second layers, since we have 5 neurons, we have 5 coefficients for the neuron, or 5 weights. We still have 1 bias. So we have 1 plus 5 parameters, which is 6 parameters. So in this model, we have 76 parameters. So if it's the first time you ever seen neural nets, you may be wondering what it is. And one easy way to understand that for beginners is that you can just view this as a very nonlinear, highly nonlinear functions of X. You want to have some prediction on the housing price, on some output, and we have 13 inputs here. We'll have a highly nonlinear function of X to make good prediction on our housing price. And this highly nonlinear function goes like this. So, okay. So next slide. So, as seen before, an NN or a neural network, even with only 3 layers, can be highly parameterized. In last example, we have 76 parameters. More generally, we can consider a neural network with k different layers. In each layers, or Z is the linear transformation of the A from last layers. And we make another nonlinear transformation of our Z. We got a new A, a new activate, which you can pass to the next layers. For L equals to 1, 2 to PK. PK is the number of neurons in layer K. Or if you like, we can write everything down in a matrix vector notation. Believe in me. So usually the matrix vector makes everything simpler. So we have some A from the layer K minus 1. We make a linear transformation which is put some huge matrix W in front of it. Z is W times A. Notice that the bias parameter are absorbed into the W2. So W is PK times PK minus 1 plus 1. So PK minus 1 is the number of activates in the last layers, and 1 here is the bias. Or Z and A are the vectors of the linear transformation and activations. Okay. Okay, so before we talk about, after you have some linear transformations or your input or your activations, you bring the transformation into some activation functions. So, what is it? Dot G is known as the activation function as the neurons in the human brain. The idea was that each neuron in the network would be a simple binary on or off. We believe that in your brain, in my brain, in everyone's brain, so there are neurons, the neuron may activate next neuron or not. So may activate the neuron, then will be 1 or be on. If it's not activate next neuron, it's be off. So the activation in human neural networks will be a simple on and off. But in the artificial neural network, in practice, we usually consider a smooth and differentiable compromise. Okay, for the purpose of fitting. In the early age of the neural nets, in 1980s or 90s, people usually consider the logistic functions, which is sigma z is 1 over 1 plus exponential minus z. So, if you know the logistic function, it will be a S-shape. So, people usually consider a S-shaped function, or if you like, you can call it a sigmoid function. But now, when people talk about sigmoid function, usually people, what people mean is the logistic function. So, the most popular activation function should be the logistic function or the sigmoid function. Somebody would like to use the tangent hyperbolic or the hyperbolic tangent, or okay, it's written as TANH. So it delivers the values between -1 and 1, so it goes like this. Some people like to use this function rather than the logistic function. Okay. But nowadays, people are making some other different choice. So the one reason people are using some other activation function because it will be easier to take the gradient, and take gradient is important in fitting the neural net. We'll talk about it when we talk about the backpropagation, the fitting part. Some people use the rectifier linear unit or the rectifier, and because it's called the rectifier linear unit, so rectify begin with RE, linear begin with L, unit begin with U, so it's also known as the RELU. Some people may just call it ReLU or something. So, or it is just the positive part function, deliver values in 0 and positive infinity. So GZ is just Z plus, which is the maximum of 0 and Z. So if z is positive, then this is z. If z is negative, then this is 0. I guess I should plot everything down. A minute, please. Okay, so we can go to my blackboard here. So we talk about the sigma e function, the sigma z, which is 1 over 1 minus z. Let me take a look at this again to make sure I make everything right. Okay. So this function will be like this. So this is our z, this is our sigma z. When z goes to infinity, this guy vanish, so it goes to 1. When z goes to minus infinity, this guy goes to this guy goes to infinity, so then the whole thing goes to 0. When z is 0, this guy is 1 half. So this point is 1 half. So this function goes like this. It will be an S shape. Or I should use another color. So it's S shaped like this. Oh man, I'm a very bad painter. Okay. And if you want to consider the ReLU, which is g of z is z plus, which is the maximization of 0 and z, the function goes like this. So if z is negative, z is less than 0, this is 0. If z is positive, then this goes like this. So it is an ReLU, or the positive part. So that's another activation function people are using now. So another activation function people like to use is the leaky ReLU, which is given some non-negative alpha. It is z plus minus alpha times z minus. We want to have this because simply because if we consider ReLU when z is negative, then this function is flat, and people want to avoid the flat spots. So that is how neural net works. So we have a linear transformation. We bring those transformations to the activation function for this layer. We got the activations, and then we bring the activations to another linear transformations. We bring the linear transformation to the activation function to the next layer, and so on. In each layers, you may have the same, identical activation functions or different activation functions. It really depends on the purpose of your work. Usually, the last transformation, the final transformation, is just the identity function, which is we have the activates, and then that is our prediction for the housing price or prediction for our output. Okay. So, if you are working on we are not trying to predict some continuous variable. We are not working on a regression type problem. We are working on a classification type problem. Usually, we will for a M class classification. Say we want to classify our something into M different kinds, M different groups. The number of output units is usually just M, and the final activation function is usually people usually call it the softmax function, which is we have the linear transformation z. You take the exponential z on the numerator, summation of the exponential z on the denominator. Then it will give some number between 0 and 1, which can be interpreted as a probability. And all n of them sum to 1. Okay, so this is what the neural net looks like. Okay, so we just talked about neural net can be viewed as a highly nonlinear model of X. We have some inputs, you bring it into a highly nonlinear model and it gives you some output. But why this specific nonlinear function, right? If you want to have a nonlinear function, it can be any kind of nonlinear function. Why we are interested in this kind of nonlinear function? It can be viewed like this. So what makes the neural net a useful econometric tool is its universal approximation property, which again is a multi-layer neural net with a large number of the hidden units can well approximate a large class of functions. Okay, let's consider a simple example. So let's consider the case with only one hidden layer. Remember, when we have one hidden layer, let's write it down. So when we have one hidden layer, let's erase it. So the ZL2, L from 1 to P2 is a linear transformation W0, WL0. 1 plus summation WL J from 1 to PXJ, and AL2, which is G of ZL2, and our Z3, which is W. You don't need to copy it. So first of all, the video will be online anywhere, and second, it is totally the same as the slides. This is W02 plus summation L from 1 to P2 WL2 times AL2, and this is our output. So we bring these two together. Our output will be this guy plus summation L from 1 to P2 WL2 times G of WL0 1 plus summation J from 1 to P, the weight from the first layer. Okay, the whole thing will be like this. Okay, and if believe me or not, it's not the first time you have seen some structure like this. Okay, so we have some output of interest on the left-hand side of the equation. Okay, then you bring some given function. You try to make up some transformation, linear or nonlinear, of your input, like this part. And you regress your output, your dependent variable, to those transformation of your x. So what's this guy? Let me put this question in another way. Let's say I just give you some I just give you some numbers, some number of W here. Some W here. I just give you some numbers here and here. And I can give you some function G. Then you bring in your X. Then you have some different G's here. You regress your dependent variable to those G. Those G is some linear or nonlinear, in this case nonlinear. These G are some nonlinear function of your X. We want to regress your dependent variable. You want to regress your dependent variable not to your X, but to some function of X. Yes, I heard somebody is talking about this. Before today, we call it basis expansion. Right. If those bases are indicator function, then you are doing regression tree. If those bases are some splines, then you are doing spline regression. If there are some natural splines, you are doing natural spline regression. If you have some W and some G, you make this regression. This is just basis expansion. Then, what's the difference between a neural net to the conventional basis expansion? In this case, those, what color do I have? Let me use blue now. In the neural net, those W here, those weights in your first layers, they are also unknown parameters. So, if you have some given values W here and here, you can fit the unknown function good. You can fit the unknown function well. Then you can treat those W as some unknown parameters. You can change the values for those parameters. Then intuitively, you can fit the unknown function even better. Let me say that again. If those values of the W here and here, if those bias and weights are given, you bring your X into a least linear transformation and least activation function, and you try to estimate the W here and here by some linear regression. Then it is simply basis expansion we talked about before in the last whole month. If this kind of basis expansion can fit the unknown function well, then now I'm telling you, you can try to also make a twist on the value of the weights, the bias here and the weights here. Those parameters are not given. Those are part of the unknown parameters. You can choose the parameters here, 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 not only these two guys, but also these two guys. Then intuitively, you can fit the unknown function even better. This, my friends, is what we call universal approximation. When these guys are fixed, the network reduced to a basis expansion. An important enhancement is that these guys and this guy, the parameters of the basis function are learned from the data. They are not given. If they are given, we are doing nothing but the basis expansion. But they are also learned from the data. So, on the one hand, we can fit the unknown function even better. When I'm talking about on the one hand, then I guess you guys are expecting on the other hand. So what's on the other hand? We can fit on the other hand, we can fit the function very good, very well, better. We can fit the function so good that we may have an overfitting problem. That's some problem we want to deal with. So neural network, it is a universal approximator. It has something called the universal approximation property. We talk about some basic idea here. If you want to know more detail Professor Kuan's review paper have a detailed treatment, and if you want to know even more details, Hornick 1991 or Baron 1993, you can find those two in the reference of Kuan 2008. Okay, so the idea is the neural net has something we call the universal approximation property. It can fit the function very well, even better than the conventional basis expansion. On the other hand, it fits the unknown function so well that we may have an overfitting problem which we want to deal with.